Okay, we'll continue with the iron carbide diagram, and we know that in iron carbon diagram, in the solid phase we have start with from y-axis we start with alpha iron, and then we have a gamma iron which is austenite, and then we have a delta iron and cementite phase which is more of iron carbides, and then we have this perlite. Just wait a minute. जी, hello. वालेकुम सलाम। अच्छा। हाँ, ठीक है, ये मतलब ये मुसीबत है। कल तो परसों मुझे कोई एक वकील साहब का फ़ोन आया, कहता आप केस कर रहे हो? मैंने कहा नहीं यार, केस क्या करना, मैं बाद में जाना। मतलब वो कहता मुझे 1000-2000 के मैं कलर कर देता हूँ, मैं क्या करना है। मुझे भी ज़ाहिर बात है, मैंने कहा तो कारोबारी ऐसे क्यों करेगा, बेचारे से गलती की हुई है। नहीं वो होगा, ज़ाहिर बात है गलती से हुआ है। चलो ठीक है, ठीक। चले मेरी अगर कोई कॉल आएगी तो मैं कह दूंगा 0324। तो अब जो है ना, मैं बता दिया करूंगा। ठीक है, चले कोई बात नहीं, चले कोई बात नहीं, चले कोई बात नहीं। जी अवैस मेरा नाम है। चले बहुत शुक्रिया। हाँ। Okay, and then we have this the combination of ferrite and cementite, or combination of austenite and cementite, just like in the form of perlite, labradorite, martensite, and bainite. Okay, this is the same as you saw in the last slides, the iron and carbide diagram, but now the detail we will do here. And you have to learn that diagram and memorize actually that diagram, because this iron carbon diagram is the important one in your coursework. So and it's normally, as we saw, that the iron from the iron ore it start with the alpha iron, which is in the solid ferrite form that contains the most of the iron content here, and we called it as a pure iron also. And as we go towards the right side, we there are more impurities we will add, and sometimes the form of iron carbide, just like the cementite form. And also when there is a more and more percentage of carbon we will add in the iron, it imparts more and more brittleness, and it change from the normal iron or steel to cast iron. It's also a good form of iron, and we know that the cast iron is a very useful form, and it can be melted and casted to different shapes, and it has very high compressive strength also, but with a low melting point. And it when its carbon contents are less or less than 2%, we can say that it's a more of a ductile iron form, and more and it's used in machining of these steels and iron alloys. And also the remaining things we have, the when we have elevated temperatures, at elevated temperatures we have, first we have austenite, then we have this delta iron and cementite form. So just to go to the more of a simplified form of that iron carbon diagram, it's in the next slide. Yes, it's written here. And we have the alpha iron on the y-axis, which contains almost 0.02% of carbon content, very very less carbon content in that. And then if the elevated temperature change into the delta iron, and the less temperature change into gamma iron or gamma plus delta iron. Okay, go into the, and just to go the detail of that ferrite, just to see the ferrite structure, it's a BCC cube, and it contains very small, as I told you, it's 0.02% of carbon only in part, but it's with the BC structure, it means that some much compact structure, solid structure of iron, but it's a pure iron, and it's a ductile and soft and magnetic properties, and we called it as alpha iron also. Then we have austenite, which is now FCC structure, and it contains higher percentage of carbon, and so it's more towards the cast, from steel to cast iron, and we called it as gamma iron. The remaining things you can read it by yourself. It's very very easy. Then we have the cementite, which is the form of iron carbide. So in the iron content, we have a much higher carbon contents are mixed with iron content. Iron is 93.3%, and the carbon content is 6.67%. It's all for the crystal structure, and it's a hard and brittle compound. Then we have this delta iron. So delta iron is also BCC, just like the alpha iron, but with a very high elevated temperature of 1390 degrees Celsius. And below this temperature, is changed into a gamma iron. Okay, and these are some different forms of iron at different elite temperature, and different percentage of carbon are given. The microcrystal structures are shown here. Okay, then the other forms, we have this perlite, bainite, magnetite out there. So in the perlite, it's a kind of a layered structure. It's composed of ferrite and cementite there, and with a percentage of 87.5 and 12.5% of by weight respectively. Okay, after perlite, we have sphaerodite also structure, and it constitutes refers to a microscopic constituent. Some steel is composed of spherically shaped cementite particles, alpha ferrite matrix. It is has higher toughness and lower hardness than perlite structure, and the microscopic structures are shown here in the figure. Then we have this bainite. This is also a plate-like microstructures that forms in steel at temperature of 125 to 550 degrees Celsius. A fine non-laminar structure, and as bainite commonly consists of cementite and dislocation-rich ferrite. It's a more strong and more ductile than perlite, but with the same hardness value. Then we have martensite. Martensite is also BCC cube, and martensite has lower density than austenite, so that martensite transform result is relatively change of volume. So all these iron forms are because of percentage of, either by percentage of carbon, or by the temperature. So normally when we change the temperature, and when we cool down, it not only relieve the stresses in the iron alloys, but it also imparts good mechanical properties. So if you want to if you want to select the material, if you want to design some machine component, or mechanical structure, we have to see the mechanical property, and these mechanical property imparts from when we have how we treat that iron structure, how we add impurities in the iron ore, and which these impurities actually imparts, and most commonly the carbon imparts some kind of characteristics, and this temperature changes also imparts the other characteristics, mechanical properties, mechanical properties of that alloys. So if we need more good mechanical properties, more higher, more toughness values, then there are some heat treatment processes we have to adopt that. So these are the heat treatment process in the next slides also. So, and the different with these heat treatment processes, actually they actually, these are controlled heating and cooling, and they induced phase transformation, and thus change in mechanical properties of the material, and these mechanical properties it produce a variety of performances in the material, because its effects is thermal treatments, and its effects is composition, its effects is microstructure, and then the result is improved mechanical properties and performance of the materials. So these are different heat treatment processes. Annealing is another one of the processes. The other is spherodizing is one of the processes, which is very similar to annealing, but just the cooling process is a bit different. It's is in spherodizing we have a rapid cooling, and in annealing we have a controlled rate of cooling. The other thing, the difference is, as we see in the full annealing, the carbon steel is heated to 40 degrees Celsius above its critical range. So AC3 line critical range is around 700 degrees Celsius. So above its critical range is 40 degrees Celsius. Above critical range means 740 degrees Celsius. So it's when it's heated in full running to 740 degrees Celsius, and we maintain that temperature for 1 hour, and then it's cooled down, but with the very slowly cool down, 20 degrees Celsius per hour we cool down, and it imparts some characteristics in the metal. And its full annealed steel is soft and ductile and with no internal stresses. So if we go to another heat treatment process, which is ferrodizing, so it's the same as annealing process. The heating is above 700 degrees Celsius, but for 30 hours, not for 1 hour, but for 30 hours. So it's there's a difference between them. So it is actually more softer metal than now came and allow more formability as compared to annealing them. So it imparts some kind of characteristics. Another process is normalizing, and in the normalizing is the temperature is just 15 degrees Celsius more than annealing process, because it is above critical line. 55 degrees Celsius means 755 degrees Celsius for 1 hour, same as 1 hour. But when it's cooling rate, so very very abrupt cooling, it is 38 degrees Celsius per minute, so very abrupt cooling rate here. So when there is abrupt cooling, it imparts some characteristics. So normalized steel has higher strength than annealed steel, but it has a relatively high strength and hardness value. Cooling cycle done is still air to avoid excessive softness in the annealing of steel. Now we have Austin tempering process, or in this process actually just like the quenching process, because let's show the quenching first. In the quenching process, actually when we heat that is heated to normalizing temperature, the carbon steel, and then it's rapidly cooled, not in air or nor not in furnace, but in water or brine solution, or maybe oil. In brine solution mean a salted water solution. So in quenching, so it imparts its more hardness and more bitterness in the material. But in Austin tempering, when it's in the molten salt metal, it is not molten salt metal at room temperature, but it is molten salt when it's dipped in molten salt. That steel, it is dipped in molten salt with a temperature of 205 to 540 degrees Celsius, then cooled at moderate rate. So the resulting steel will be a bainite, and it has greater ductility and high impact resistance and less distortion than martensite steel. So this is about Austen tempering. Heat treatment processes. These are very, very important heat treatment processes. Actually, it imparts the mechanical properties. Then the tempering, most commonly used, and it imparts more ductility, more malleability, and it reduces the hardness and the brittleness of the material, and it also reduces the residual stresses and increase the ductility and toughness of previously hardened steel. Actually, this tempering, actually we do it, tempering and case hardening. Normally these processes we do when we have, there is a previous heat treatment process are there, and then some properties we want to improve more, then we will do these kind of process. And commonly used, we normally the when we component that normally machined, or machine tool we used, or they have the tools and workpieces normally tempered to improve its ductility and reduce the residual stresses that are available in the workpiece and in the tool. So also the case hardening process, in which the outer case of the workpiece is only hardened, and the inner side, we will prevent inner side as tough or ductile interior will be remain there. So okay, these are different heat treatment processes, and very very important processes. You have to know these processes, and normally these things, iron carbon diagram and heat treatment process, just read out and memorize, and not much conceptual thing there in that. Hope you understand well, and okay, thank you very much. We will end here.